Good evening and welcome to this session on a very important chapter called solid state. Like most of you already know, the previous few weeks we've been actually looking at chapters from class 11, and for a change we want to be able to help students in class 12 as well. So this time we start with a very important chapter called solid state, and if you look at this chapter called states of matter from class 11, we kind of had an abrupt ending, as in we didn't discuss that chapter called states of matter face to face yet. We'll do it in some time. But if you look at that chapter, or if you've had the chance to look at that chapter, then you will see that that chapter deals with the gaseous state and liquid state. So, and it largely deals with gaseous state, and in that chapter you actually don't encounter the solid state. So this chapter is an attempt to explain how solids are arranged in terms of their molecular structure, or at the atomic level how they are arranged. So to start with, in each session I've been giving a mantra. So what is the mantra for this chapter? So definitely this is a very scoring chapter. So the mantra is thou shalt score always. So if you look at the different kinds of questions that you get in this chapter, you get two different kinds of questions. One is the very simple, easy, straightforward question completely based on theory. So it could be from Schottky defect, Frenkel defect, that kind of a thing, or it could be based on any of the types of unit cells, or any of the 14 Dravai lattices, and so on and so forth. So these are things that you have to just keep in mind. You have to actually memorize these things. Now that is not to say that you won't be able to understand the complexity, the mathematical complexity behind these crystal structures or their geometries, but even if you don't understand, you are still in a very good place as far as memorizing these things that need to be kept in mind, as in the things that need to be memorized or learned by rote. So that is one type of question. And on the other hand, you actually have numericals. So when I say numericals of a number of types, they'll ask you to find the radius ratio, or they'll ask you to find the type of the crystal lattice, or they could actually they'll ask you to find out the number of voids, or the distance of the voids from a point in the crystal lattice, so on and so forth, the density of the lattice, the edge length. I mean, you can just play around with any number. Basically this chapter has that one particular formula, okay, density based on the other parameters like atomic radius or edge length. So based on that, and Avogadro number, so you have that one particular formula, and based on that there are a number of different types of numericals that we actually get. The other type of numerical that you might encounter in this chapter happens to be the one having radius ratios and stuff. You have a different ionic crystals, structures like NaCl, or a slightly variation, a small variation on that, a twist to the NaCl structure, and that would be actually cesium fluoride structure, where you have variances in terms of the radius ratios. And you also have the fluorite and antifluorite structures, and the two different types of zinc blood structures as well. So based on these set in stone, very predictable kind of very formulaic methodical approach, you get problems that you can actually expect. There is not much variety in terms of how difficult a problem can get. So these are broadly the two different types of questions. On the one hand, you have things that require rote memorization, things that you just need to keep in mind, a property of Frenkel defect, or where it is applicable, or something to do with conduction band, things that you have to just memorize, and whether or not you understand, you'll still be able to crack those kinds of problems, because basically they'll ask you what kind of defect is shown in this picture. So it will be one of those 3 or 4 defects that you have come to notice. It could be Frenkel, Schottky, non-stoichiometric, and so on and so forth. So either the cation is in excess, or there are different varieties there. So either that kind of question is there, or you have a numerical. So on top of this, very rarely you will get a question which tests your spatial understanding, spatial reasoning of how atoms or ions are arranged. As far as JEE Advanced is concerned, it's been very rare that you get out and out theory based question. But as a surprise, I think in the last 4 or 5 years they had this one particular question which was based on the 7 types of unit lattices. So basically they had, you have those 7 different types: cubic, rhombohedral, orthorhombic, and so on and so forth, triclinic, monoclinic. So based on those parameters, you have, edge lengths A, B, C, whether they are equal or not, and the 3 different angles. So based on that, there was a problem. And apart from that, probably there have not been, that many questions which completely only was, based on theory. I do remember, I vaguely remember, I can recollect a question which talked about a plane, probably in an FCC structure, at the 3rd atom in a unit cell. They've given different layers, and the 3rd layer would go through how many different atoms, that kind of a question. So that would of course test your spatial understanding of how the whole thing actually works. So from purely from one particular edge of an FCC unit cell, if you look at it, what kind of layer arrangement that you are likely to encounter, that kind of a question, it belongs to the realm or the domain of spatial reasoning. So that happens to be the toughest kind of questions. So broadly speaking, these are the 3 types, the first 2 types being the most common. Okay, so where do we start with this chapter? Of course, obviously you'll have to get your basics right, and probably in the whole of chemistry, okay, 11th, 12th, probably all 12 years of learning science put together, if there is one chapter where there is enormous scope for animation and using 3D models and actually absorbing and imbibing stuff by looking at a 3D model, this is that chapter. So this is the chapter where you have a maximum bang for your buck, maximum value for the money that you invest in terms of learning from advanced technology. So we at the BYJU'S learning app, if you have a chance to take a look at our chapter or our interpretation of this chapter, even if I say so myself, it's come out really spectacularly. I know you can just see everything going on. We actually shift and rotate and literally show you how an unit cell looks like from different vantage points, how different layers have been lowered one on top of each other to give rise to that particular unit cell, which if you propagate by means of translational repetition, you can actually get to the entire crystal, so to speak. So well, if you don't buy my sales pitch, then probably you can actually take a look at any of the university websites where they have a JMOL or a different kind of JavaScript based technology where you can actually visualize and play around with with that crystal structure. So that such things are available if you actually go around looking for them. So well, to each his own. So you can actually look at these ready-made available models which actually help you visualize in a much better way than say when you actually look at a 3D structure and try to rack your brains and figure out which atom or which lattice point belongs at which point, because you have the disadvantage of trying to interpret a 3D thing looking at a flat 2D image. Of course, I mean, it might be a very colorful image with a lot of different hatchings and stuff to be able to give you different perspectives, but still, I mean, they say that a picture speaks louder than 1,000 words, but a 3D model is infinitely better, is what I would say. Yeah, that's that. So if you're just going to read from a book and methodically try to remember stuff, many students actually have a good success ratio doing that as well. So I wouldn't dissuade or discourage people from doing that, but you put in so much effort to remember stuff, you have to keep refreshing that so that you don't actually forget. There is just so much more rote learning involved in this chapter than any other physical chemistry chapter, barring maybe something like surface chemistry or some such thing. But I would say that instead of rote learning, use technology, use our app, or use any of the university websites which have that kind of technology, so you can actually visualize how things are arranged in 3-dimensional space. So just mugging up formulae might work. It works for a lot of people, but of course, I mean, if you want to leave your admission or your candidature into an unknown variable, be my guest. Next up, let's quickly take let me just quickly take you through the important parts of this particular chapter. So like I said, get your basics right. We start with classification of solids. I've never ever encountered a competitive examination question based on classification of solids, something as simple as amorphous or crystalline, or properties of these. this is not to say that you will never ever get a question, but it is just that I couldn't recollect, which means there is a likelihood that it is not that common. Solid state, it belongs to the realm of physical chemistry, so you get proper physical chemistry based questions, the three types that I had elaborated before. Okay, so of course, once again, classification of solids could also happen in terms of ionic solids, covalent solids, metallic solids, or molecular or even network solids. So different properties of these, compare and contrast, and which has a higher melting point, which doesn't have as much of a higher melting point, which falls where in that realm, in that trend, so to speak. So properties, examples of these things you should definitely know, and take care of your understanding of definitions like lattice or space lattice points, and what is a unit cell, and how the molecular or the geometrical arrangement of a unit cell largely determines the properties of the crystal itself. So is there a correlation in their shapes? So for instance, if one is actually a cubic thing, can the crystal, if the unit cell is a cubic thing, then can the crystal be actually cubic, or can it be anything else? So if there is a correlation, if there is a mirroring of properties, so go into that. You should have a basic idea, because this is one small conceptual area in this in this realm of a lot of jargon and definitions that you might get tested in. So having said that, there are 7 basic types of primitive unit cells. So invariably, some books, they do start with elements of symmetry, but elements of symmetry becomes a little high-handed and it becomes a little tough. Especially in solid state, elements of symmetry is best appreciated using the current latest technology. If you don't have access to a software or a tool which helps you look at a unit cell and figure out the different elements of symmetry, the points of symmetry, axes of symmetry, planes of symmetry, and so on and so forth, centers of symmetry, and so on and so forth. So if you can't figure out the elements of symmetry with the help of such a tool, then I wouldn't actually venture into spending so much time, energy into actually figuring out and imagining the elements of symmetry. That becomes a mathematical exploration by itself. So I think that is not where we should spend too much time in. So maybe if you ask my personal opinion, then probably I wouldn't start this chapter with elements of symmetry. Maybe I can give a basic introduction, but I wouldn't spend a lot of time, effort into that, and build it from that, because neither you, to be honest, nor me, we have the right kind of mathematical background to be able to appreciate solid state physics. So in fact, that course is actually taught at the graduate or postgraduate level. Okay, so once again, getting back, so there are there is something called elements of symmetry. From there, the theory actually flows into 7 basic types of primitive unit cells. They are cubic, tetragonal, orthorhombic, rhombohedral, triclinic, monoclinic, hexagonal, and definitely you should mug up the parameters of these 7 types of primitive unit cells, A, B, C, how they are. For instance, if it is cubic, if A equals B equals C, alpha equals beta equals gamma, all the angles are equal to in turn 90 degrees, and so on and so forth. If you take I think a triclinic, none of them will be equal. So instead of all the equality, you just replace them with inequality, and then you will actually get triclinic. So what is rhombohedral, orthorhombic, tetragonal, and so on and so forth. So among these, if I were to raise a question saying, in how many of these 7 types of primitive unit cells, we have 2 sides equal to each other, but not equal to the third side, but neither of them is equal to the third side. So if I were to probe your rote memorization skills, so to speak, based on those parameters, then probably you should be in a good place to answer them, because this definitely came in one of those JEE advanced questions, which means now this becomes fair game for all the other exams like NEET and JEE mains and BITSAT and whatnot. Yeah, so without going into the mathematics part of it, I'll just tell you outright that there are 14 types of Bravais lattices. This is because, if you are interested in the mathematics, this is because not all crystals are simple. Some are total number of space lattices of all 7 crystal systems equals 14, because there are 7 simple types, simple ones, and then there are ones which have body centers, and there are ones which have face centers. So those things are also applicable. So 7 types of basic or primitive unit cells and 14 Bravais lattices. You need to remember this. You need to remember the parameters of for the 7 things. Okay, so that's that. So this takes care of the introduction part of solid state. Next up, of the 14 types, so you need to know how many are simple or cubic, how many are FCC, and how many belong to the realm of body centered cubic. So we are, of course, right now when I say simple, cubic, FCC, BCC, we are only talking about cubic systems, which is a subset of the 14 types of Bravais lattices, isn't it? Yeah. So the type of lattice point and the contribution to the unit cell. So where is the lattice point actually there in the unit cell? Is it in the center, on the center of an edge, or is it bang on the on the center of a face? Is it at the body center? Is it at the vertex, one of the 8 vertices, and so on and so forth? So that also comes into picture. And when you say that when you have an atom which is shared by 2 adjacent unit cells, such that the atom is in the face center, so that particular atom, it contributes half an atom to each of these 2 unit cells. So if there are 6 such atoms at the face centers, at the 6 face centers of one unit cell, you should be able to calculate the total number of atoms within that unit cell. Okay, because it is shared by 2 things. So let us assume in this plane there is an atom. It is shared by the cell above and the one beneath. So it is going to be shared by 2 of them. So of course I'm building castles in air, please bear with me, but that's the big disadvantage about this chapter. Even a very good teacher is only so effective, because without the right kind of tools, it would be really impossible for people to actually imagine. And given that different students, teachers, and even from the public domain, the general people per se, they also have different people have different kinds of difficulties in terms of understanding how things are arranged in space. Spatial intelligence, that gets tested in this chapter. That's the point I'm trying so hard to make. Okay, so also if you look at these cubic systems, you should be able to figure out the relationship between the edge length of a unit cell and the atomic radius. Yes, for simple cubic, atomic radius is 0.5 times a, which is the edge length. For BCC, it would be root 3 a by 4, and for FCC it will be 1 by 2 root 2, the whole times multiplied by a, and so on and so forth. So all these formulae, all these results, you should be able to readily recollect at an instant. That's also something which is very, very important, because if you end up spending valuable time in your competitive examination trying to derive and imagine the whole thing once again, and if that also contributes to your that increases your chances of making an error. So don't do that. As far as the theory part of this particular chapter is concerned, definitely you will have to keep a lot of things in mind. For instance, these results. You should also be able to calculate the number of atoms per unit cell. Once again, that is something that I have underscored. And you should get the definition of packing fraction. Okay, so in a unit cell, there is a volume occupied by the edges. There is a theoretical volume of that particular unit cell itself. So within that unit cell, how much of the space is occupied by the number of atoms of that particular unit cell? So that is going to be your packing fraction. So for simple cubic, it's going to be 0.52 or 52%, which means 48% is empty. For FCC, it has the most efficient packing at 74%, and which means that remaining 26% is empty space or voids. And for body centered cubic, I'm only talking about cubic structures here. So BCC, the packing efficiency or packing fraction happens to be 68%. Yeah, so obviously among the 3, it's going to be FCC which takes the cake. That is the most efficient, simple cubic being the least efficient of the 3. So all these things, you should be able to derive them, but at the same time, you should still be able to figure out, and you should still be able to recall instantly these numbers, the numbers that I'm actually spouting out. So with practice, it will get easier. We teachers do tend to forget sometimes, so that's that. Next up, you should understand the basic concept behind closed packing of spheres. Suppose I were to arrange 2 rows of spheres, so I could arrange such that the space between the voids between 4 four spheres which are almost arranged at the edges of a square, the void between them could be either the greatest, or if I actually slightly skew one layer such that the sphere from the first layer is in between, is in the gap, it corresponds with the gap, or it is aligned, or it is juxtaposed just adjacent to the space between two adjacent spheres in the second layer. So I'm putting the first sphere in the gap between two spheres from the next layer, and this arrangement continues. That would be closed packing in 2 dimensions. Now if it were happen in 3 dimensions, so how would that be? Now this becomes incredibly difficult in terms of visualizing, but there are some effective, efficient methods, some tools. Even from books you will be able to actually appreciate, you will be able to figure out, for hexagonal closed packing you'll be having A B arrangement, or for the other one, as in cubic closed packing, you'll be having ABC, and then the 4th layer will mirror the first layer. So every 4th layer will be the same as the layer that we are starting with. So second would actually correspond with A, B, C, A. 4th layer is A. So 5th layer will actually correspond with B, 6th layer will correspond with C, and so on and so forth. So here, of course, obviously your understanding of voids, what kinds of voids are there, how to give rise to a tetrahedral void, and how do we get to an octahedral void, that becomes very essential for you to be able to follow this AB in HCP, or ABC in CCP, or FCC for that matter. And of course you need to remember the examples for these these crystal structures. For instance, if you want AB or HCP, then you have something like magnesium, zinc, molybdenum, vanadium, cadmium. These are the examples. And as far as CCP is concerned, you have the precious metals, copper, silver, gold, nickel and platinum, nickel being the exception of the precious metal, so to speak. And as far as BCC is concerned, then you have alkali and one or the other alkaline earth metal, something like barium. So lithium, sodium, potassium, rubidium, cesium, and barium. So these are all actually BCC examples, aren't they? So once again, like I said, voids. What are voids? If you want to visualize a tetrahedral void, take 3 spheres, they are of equal radius, they are touching each other. Okay, so there will be an empty space just at the center. So it's actually a 3-dimensional space. Obviously I'm talking about spheres, not circles. Okay, sphere 1, sphere 2, sphere 3, there is a space. Right in that space you put a 4th sphere. Yeah, so it would give rise to a tetrahedron. Yeah, so the void there is actually called a tetrahedral void. So likewise we start with 3 spheres, okay, such that first sphere is closer to me, the other 2 are closer to you. Now I copy this layer on top and I rotate it by 180 degrees and then lower the 2. Okay, so I have 1, 2, 3, and the image of 1 will be here closer to you, and whereas 2 dash and 3 dash, so 1 dash is closer to you, 2 dash, 3 dash, the images, I'm using a physics reference. So if I lower this, so 3 spheres like this, the other exact opposite, twisted by 180 degrees and then lowered, that would actually give rise to an octahedral void. Yes, and you should be able to figure out the sizes by I think by even an intuitive understanding would tell you that probably tetrahedral void is bigger. So that's that. So you need to be able to imagine, visualize in the 3-dimensional space, and under exam pressure you should be able to visualize, given a unit structure, given a unit cell, you should be able to figure out where are the octahedral voids, where are the tetrahedral voids, and all those things, and the distance of a tetrahedral void from a particular lattice point. It could be any lattice point. So that's also something which is very, very important. Next up, we have different kinds of numericals. So the last part is going to be actually you have different types of ionic solids, right? You have like solids like NaCl, and how the ions are arranged in a crystal lattice of an NaCl structure. That is actually very important. So which is the larger ion? Is it the cation? Is it the anion? And what is the radius ratio? And based on this, in a unit cell, the smaller ion, it has to occupy some space. So that space where in fact how the smaller ions are arranged around the bigger ions will actually be a function of the radius ratio, isn't it? So based on the radius ratio, we can actually figure out, you should be able to figure out, know and reduce as to what kind of voids that ions get occupied. Now I'm not talking only about NaCl, I'm just talking about a general scenario. So different types of crystals, NaCl crystal. So if there is an NaCl or NaCl type of crystal, then you should be very familiar with how the whole numerical could be asked, in what variants can the numerical be twisted, and you should be able to remember the parameters like the radius ratio, the coordination number. One Na plus is surrounded by this many Cl minus, and one Cl minus is surrounded by this many Na plus ions, and so on and so forth. That is very, very crucial. So NaCl type, and similarly CSCl type, okay, where you have 8:8, so that kind of an arrangement, and how the packing fraction, how packing fraction becomes a function of the radius ratios between these types of crystals. That is also something which is very important. Zinc sulfide structure has two different varieties, two variations, as in one is the blend structure, zinc blend structure, and the other is the woodside structure, is it not? So once again, maybe, yeah, of course, I mean, you should remember some examples for both, what are the differences between the two, and so on and so forth. The other things that are very important happen to be the fluoride structure, the antifluoride structure. Once again, all the other parameters like NaCl, CSCl, zinc sulfide, fluoride and antifluoride, you will have to remember all the different parameters, the different types of numericals that you could possibly encounter given this this framework. For instance, in chess, many grandmasters actually, they know the first 22 moves, how the first 22 moves will actually pan out in a particular opening of chess. It could be King's Indian Defense or Grunfeld or whatever. Okay, so how the initial moves happen, how the white pieces move, and what would the response of the black pieces be, or what array of responses could there be. Okay, so they have all these things in their heads. I mean, they can recall it, they can just play it out of sleep. They don't even need to think about it, the first initial few moves, and then it explodes into complexity. We are digressing. So as far as these structures are concerned, the variety of numericals that you encounter, those things are pretty important. Lastly, I probably left out the memory intensive rote learning mug up kind of stuff, where you have defects, Schottky, Frenkel, and you have even conduction in solids. So those things I probably left out because there is not much. I wouldn't even want to answer questions on that because it's just very plain boring. One Google search or one flip through your book, and you already know what to answer, what you're looking for. Yeah. So let me see if we can have any questions. Once again, Siva Surya, he's asking what are metal excess defects. Very simple. I mean, yeah, let's not discuss defects because one Google search, you already know what Schottky, Frenkel, non-stoichiometric and all these things are. Everything is a one-line answer. Sometimes you have the cation in the excess, sometimes the anion is in excess, sometimes you have holes, and sometimes you have something which is there supposed to be in the void is not there, and so on and so forth. So we'll leave that out. I think we've actually come to the end of this session because we don't have any more questions, or I couldn't see any more. So with that, we wrap up this session on solid state. Yeah, thank you.